Good day, and welcome to today's Electronic Design webcast. Our topic today, precision magnetics, solving the stability challenge in isolated current sensing, sponsored by Texas Instruments. I'm Bill Wong, Senior Content Director with Endeavor's Design Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your question during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your question into the question window on the side of your screen and hit the Submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Stephen Loveless is the product definer for TI's magnetic current sensing product portfolio. His responsibilities include driving key customer engagements, aligning the product roadmap to future demands, and acting as technical expert for magnetic current sensors. His primary focus is to act as the voice of the customer within the product development process and the direct R&D efforts on technically differentiated magnetic products to solve today's evolving isolated current sensing challenges. You can learn more about our speaker by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenter. Stephen, the floor is yours.
All right, thanks, Bill, and thank you everyone for joining today. I'm going to jump right into it, and today primarily we're talking about isolated current sensing and the key challenges that happen in the space and ways that IC manufacturers like Texas Instruments can help solve those challenges. Primarily when we talk about isolated current sensing, we can kind of break these key needs down into three buckets. First is the implementation challenges, right? And these are kind of the simple design decisions that you have to make whenever you're choosing a current sensor. Things like what environment can the current sensor go into? What is my signal chain around the sense element? How much calibration do I have to do at system level, as well as things as simple as, what does it cost and what kind of components do I have to have around it? Secondly is really the sensing element, right? Is how accurate of a measurement of my current do I actually get? This includes both initial tolerances as well as the lifetime drift, the drift over temperature, and the dynamic range of the measurement, right? There's a lot of considerations here. And then as far as isolation, this is a key figure that you either have to hit for a given system or you don't work in that solution, right? So things like lifetime operational voltages, as well as dynamic events, surge events, or overvoltage events that you have to be able to survive. And so, how a certain solution fits into those three buckets is what we're primarily talking about here today. And in general, TI, we categorize these solutions for isolated current sensing into four main buckets. So we have isolated shunt solutions, where you take a shunt-based resistive measurement to sense the current on an isolated net. And this typically provides high accuracy, low drift measurements, relatively low noise for both AC and DC currents. The challenge being that you have to have the external components, namely the shunt, as well as sometimes some isolated supply, and it takes up a moderate amount of board space. And then you have current transformers, or CTs, that take AC measurements only. And CTs, there's a wide range of different CTs that I'm sure many of you use. And the key challenges here is that CT dominates really both the cost, the accuracy, and the form factor. So that component itself is pretty critical. And then in magnetics, we really have two different categories. We have contactless magnetics, where you're not actually touching the isolated net and you're taking simply a field measurement. It typically, the magnetic design and the mechanical design controls both the form factor, the cost, as well as the accuracy, and does require some external components. And then we have what we're primarily going to talk about today, which is what we call in-package magnetics, which is where the current that you're measuring on an isolated net actually flows through the package of the IC itself. And this allows you to have a small form factor as well as utilize a single component for both AC and DC measurements, but typically has some challenges in terms of isolation as well as the drift of that system and the accuracy that you can accomplish over both lifetime and temperature. So for in-package magnetic current sensing, what I'll abbreviate as MCS here, fundamentally the current flows through the IC itself, through the IC package and through a copper lead frame that's internal to the package. And this copper lead frame is electrically isolated from the die with galvanic insulation. And that current flowing through a loop or a geometry in the lead frame actually creates a concentrated magnetic field. And that magnetic field, nice physical law, is proportional to the current itself. And by placing that IC above that loop, you can actually use a Hall effect sensor to convert that magnetic field into voltage. And this voltage is then isolated from the sense net, as well as gives you a nice convenient signal for the rest of your system implementation. The real benefit of these is that the signal flow itself undergoes a domain transformation. So you have current flowing into and out of this lead frame loop, right? And that's an electrical signal. And that's within the package construction itself. There's several signals coming from that isolated net, right? You have your high voltage common mode. So if it's a DC signal, this is sitting on your DC bus, maybe a 400 volt DC bus. And internal to the package, we have an isolation barrier that effectively blocks that common mode. And then also you might have some high frequency or high DVDT transients, right, with a lot of spectral content. And actually on the isolated die, TI puts a capacitive shield on that die so that we can absorb those DVDT transients to block that high frequency content. So in the end, the only signal that actually gets to the sensor itself from the isolated net is the magnetic field generated by the lead frame loop. And so the key benefit of this is that you have really good common mode rejection and transient immunity, because that electrical signal gets blocked either in the package or in the shield on the die, which means you can directly measure AC or DC currents with a completely passive front end, right? Because there's no electrical coupling, you don't need an external shunt, you don't need an external transformer, and you also don't need any isolated supplies because there is no active circuitry on the isolated side. And on that die, that sensor die, the key there is how good of a precision Hall sensor can you make to measure this magnetic field, right? So typically you have a Hall sensor, and with the magnetic fields that we're talking about, Hall sensors generate relatively small signals, typically in the microvolts to hundreds of microvolts level. And so the key there is, do you have a good precision analog front end, or AFE, and signal chain to amplify that signal with good signal integrity and dynamic range to get to a full-scale voltage output. In our lead device, that can be 5 volts down to 3 volts. And the key there is, can this AFE compensate the Hall sensor for Hall sensor variation and drift over time and temperature? And the benefit of this topology really is that you get a full-scale analog output voltage, right? It looks and feels kind of like an amplifier. It's a low impedance voltage output that integrates easy with typical ADC signal chains. And also that AFE and signal chain can be tuned specifically to that Hall sensor as well as to the package. So you can calibrate and compensate the whole system in one solution, and then it's a canned, ready-to-go solution for a customer to implement on a board. So those key benefits kind of map to 2 really specific applications, right? One is for measuring inline PWM signals and things like inverters that might drive an inductive load like a motor, or are generating a 60 hertz AC output through a filter. And the benefit here is that high common mode rejection and CMTI eliminates coupling from the PWM voltage transients into your signal chain. So you don't have to worry as much about sampling coherency and trying to catch a specific point in a PWM. Another application that benefits from this type of architecture and implementation is simply doing some isolated AC or DC current sensing, right, on either a high voltage bus or directly on AC line. And that's really because you don't need any hot side components to do that direct sensing. So you don't need any other components on that isolated net, and you get a good, clean analog signal out. And common among these two is really that, first of all, that need for isolation. There's inherent galvanic isolation here, so you can tolerate high voltage as well as high voltage transients. And really, it's a small solution size because you don't need any external components that kind of makes it easy to use. As well, there's low power loss because, again, you don't have a supply on the hot side consuming any power, as well as the lead frame itself is relatively low ohmic, so you don't have a lot of power loss from something like a shunt. Outside of the integration and the implementation, the sensor architecture itself really impacts the system level performance and how you design the system signal chain. So TI has released two devices in the last month or so, the TMCS 1100 and 1101 as our first products in this space. The TMCS 1100 can tolerate 600 volt isolation for direct connection to a number of either sources or loads, things like AC line, high voltage batteries, or directly monitoring motor currents. And it can tolerate high switching transients, so greater than 50 kV per microsecond. And this is what gives you a good clean output signal, even in the presence of a lot of voltage variation or PWM edges on the input. Also, TI took a little bit different approach with the sensor itself. We actually made a single device supply capable from 3 to 5.5 volts. So the same device works no matter what your supply voltage is in any particular system. As well, the sensitivity of the device or the gain of the device is fixed, which means it doesn't vary by the supply. And what this gives you is it gives you high PSRR for noisy environments, as well as if you have a bad or a switch mode power supply that has some bad ripple on the supply, you don't see that show up in your output sensitivity. The TMCS 1100 has an external reference that defines your 0 amp output voltage. So that's basically the offset of the output. And that lets you generate custom dynamic ranges or directly match to the mid-scale of your ADC. The TMCS 1101 is a similar product, but just integrates the reference into the silicon itself so that you don't have to provide that external reference. And that just simplifies the design, although it somewhat limits the flexibility relative to the TMCS 1100. And both of these devices are in an SOIC 8 package, so it's a compact form factor for up to 600 volt sensing. Historically, I mentioned this a little earlier, the biggest challenge with magnetic sensors, and specifically Hall sensors, is that they have a lot of inherent drift and nonlinearity. Primarily, this is due to the temperature and stress coefficients of the sensitivity of a Hall sensor. And what this leads to is it leads to performance variation both over temperature as well as time with package hysteresis and drift. And I show here a relatively old paper from 2004 just highlighting the kind of drift that most Hall sensors can pretty easily observe, right? Is that over temperature along the x-axis from -50 to, I think this goes to 180, you could see about 6% sensitivity variation of the sensor. And the key thing is that there's also a lifetime effect or a hysteresis effect that the sensitivity shifts both when it comes directly out of fabrication as well as over the lifetime of the product. And this has been a key challenge. The industry has tried to address this in two key primary ways. One is just with linear correction at the factory or test and trim. The challenge there is that you cannot compensate for non-time zero effects. So you cannot compensate for package hysteresis or aging of the sensor itself. And so typically that limits you to about 2 to 3% sensitivity accuracy across temperature and across the lifetime of the product. The other approach is to actually allow users or customers to program the compensation at system level. The challenge there is that it requires system level calibration. You as the customer have to test the sensor and then calibrate it either on chip or at system level. So really that's limited by customer capability both to test as well as the cost of that implementation at system level and in manufacturing. What TI has done with the TMCS 1100 is try to innovate in the way that these sensors are compensated by adding in situ compensation on the IC itself, as well as pairing that with the zero drift analog front end architecture. And this allows us to do a high precision factory calibration at time zero, and then the circuit itself compensates and continually adjusts for temperature, stress, and aging that eliminates most of these package hysteresis and lifetime effects, as well as greatly improves the temperature performance of the chip. And this is really enabled by TI's precision signal chain technology, both in circuit design as well as in our process technology to build more stable analog front ends and Hall sensors. When we look at the accuracy of a sensor, we talk about several different accuracy specifications before I get there. Generally a sensor is considered a linear transfer function. You have current in, you get voltage out. And we have a couple specs that relate to that. Sensitivity is simply the gain or the slope of that transfer function, and offset is, of course, the offset in the y direction. What is your output when you have 0 amps as opposed to the ideal output? And both of those parameters also have drift, both in time and in temperature. There are some second-order effects as well. There's nonlinearity, that your sensitivity might change as a function of the input current. And then operating condition errors like power supply rejection, common mode rejection, and reference rejection. And these are all, if other system-level operating conditions change, you see an additional error due to those. The combination of all those, as well as errors from external fields and from other things, give you a total error curve that is really what a customer ultimately cares about, because that's how the sensor is going to perform in the system. When we look at total error calculations for the TMCS 1100, and I've shown the datasheet specs here for all those errors that we just referenced. Typically, we like to look at this as total error versus input current, because it's not just the full scale or maximum current error that you care about. For example, here I've shown the TMCS 1100A2, which is suited for bidirectional 20 amp measurements. And you can see that the full scale error from -40 to 85C is less than 1% at 20 amps. It's 0.93%. But what you care about is not only that, but the dynamic range of the sensor. And so that's the key thing to look at this total error curve. And so here we have the room temp, -40 to 85, -40 to 125, as well as if you do a single point calibration at room temperature simply to remove the offset errors, the time zero offset errors, and that's the curve in red. And so what we can see here, which is really the innovation in the sensor, is that even with just a 1-point room temp calibration, you can achieve less than 2% total error across 90% of the sensor's dynamic range, all the way from about 2 amps to 20 amps. And this is across temperature as well as across time. When we go to the next challenge, which is really the isolation of these products, because of the construction of these, where you have an IC mounted above a lead frame, that vertical separation between the lead frame and the die is actually your insulation barrier. And we specify that barrier in multiple ways. And primarily, all of these are simply different specs for different stress conditions. We always try to specify what the expected lifetime survivability to that particular condition is. For lifetime constant working voltages, we use the maximum repetitive voltage or the maximum working voltage. And these are 100+ year type ratings. For the TMCS 1100 family, that's 424 volts RMS if a bimodal AC signal, or 600 volts peak if it's a transient signal or a DC voltage on the input. For transients, the common spec is 60-second survivability. This is consistent with the UL 1577 standard, as well as with several IEC system level standards for the electrical strength test of the device. And for the TMCS 1100 and 1101, these devices are specified to survive 3000 volts RMS, or a little over 4.2 kV peak, for greater than 60 seconds. And then we also have the maximum surge isolation voltage, which is really for highly dynamic events like lightning strikes or system level surge testing. And the TMCS 1100 is specified to survive 50 of the IEC standard 1.2 50 microsecond surges at 6 kV peak. And for TI isolation, TI has a wide portfolio of isolation products and technologies. And one thing we've done with this device is try to improve the way that quality and reliability are built in to the product itself. TI is the only supplier to actually provide installation lifetime expectations for these products. And we do this via a TDDB curve, which is a time-dependent dielectric breakdown. And this curve is shown here on the left. It's also in the data sheet for every product. It tells you for a given stress voltage on the x-axis, what is the expected lifetime of the product before you hit a specific fail rate. In the case of the TMCS 1100, you can see this dark green box is actually where we specify the product at 424 volts RMS AC stress voltage. So if you go all the way up that curve and see where it intersects the dark or the black curve, you can see that the expected lifetime for this product is actually well over 1,000 years. It's a very high quality barrier, and TI is relatively conservative in the way that we spec isolation products. What you also see is this light green box is actually the VDE 0884-11 margin requirements, and TI is the only provider to actually specify all devices per VDE 0884-11, which is one of the strictest component level standards. And the main way we accomplish this is by high testing quality and very rigorous screens. The industry requires about 900 volts partial discharge, which is the insulation quality testing. And TI actually tests these products at 3.6 kV, so that we test significantly above any operational levels to ensure that we hit high quality and a high reliability barrier. So to kind of summarize and wrap us up before we go to questions, we've talked about these three key challenges. On the implementation side, we've seen that in-package magnetic current sensors provide a pretty simplified single element sensing solution. And the change in the architecture that TI has done with the TMCS 1100 really improves that cost performance trade-off that we see in this space. From accuracy perspective, right, there's tight factory calibration, and TI has really enabled this tight factory calibration to last over time and temperature, both with the zero drift signal chain technology as well as real-time sensor compensation on the circuit itself. And then for isolation, the key here is really building in that lifetime isolation quality through rigorous screening. And even with this rigorous screening, TI is still able to give you optimized 600 volt isolation in the SOIC 8 package, which really optimizes the PCB form factor that you can still use for high voltage sensing. And with that, I will open the floor to questions. Bill?
Okay. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So the first question, are external magnetic fields a problem?
So external magnetic fields can cause a signal on the sensor. And so that can create a problem with your current measurement. If you look back at the table that I showed the calculations for total error, in the small text, and we can maybe check it in the version you look at the email, I actually assumed a magnetic field about equivalent to what you would measure for Earth's magnetic field in a random lab. So it does create a small error signal in the sensor, but the sensor itself has such a higher coupling for higher currents that it's a relatively small error, but it is something that needs to be considered at system level.
Okay, could you make a suggestion for measurements regarding or in the range of 28 volts DC at 1,000 amps?
So for 28 volts DC and 1,000 amps, there's actually a couple different solutions you can go with here. You could go with a contactless magnetic solution, and that allows for low power loss on that 1,000 amps. But for 28 volts DC, you don't actually need a completely isolated solution. So actually there's some pretty good shunt options there too. TI also offers some very high precision current shunt amplifiers with very low offset voltages down in the microvolt level. And that allows you to use a very, very low ohmic shunt and still measure high currents. So you really have multiple options there to go with.
Okay. Could you comment on the current range for AC/DC?
So the current range for AC and DC measurements, so the measurable range is determined by the sensitivity of the sensor and the full scale output. So the TMCS 1100A1 is our largest current range device. It has a sensitivity of 50 millivolts per amp. So if you have a 5-volt output and you're measuring AC signal, right? So you need to see both positive and negative. That device can measure, its measurable range is a little under 50 amps in both directions, bipolar. And really that can go down to our TMCS 1100A4 has our highest sensitivity for the smallest currents, and that's 400 millivolts per amp. And so that device is optimized for measuring currents in the 4 to 5 amp range. So really this particular product is targeted for measurements between 4 and 50 amps peak.
Okay. How can you reduce errors if the total current range is 5 amps?
Right, so at 5 amps, the key thing here is that at that low of a current, the offset errors will probably dominate your total error in a system. Now, there's not a whole lot you can do to improve the particular offset error of any device. So there, it's really just about choosing the device with the lowest offset error and the lowest offset drift. The TMCS 1100, if we look back at its data sheet specifications, and I'll see if I can push this, has an offset error of about 30 milliamps. So that's basically the dynamic range, is that you're going to see a lot of error under 30 milliamps. But what we see is that the 1100 overall has the lowest offset drift. And so what that means is that if you do a 1-point calibration, that's probably the best way to optimize a lower current measurement like that.
Okay. Is the device protected against fault currents of, say, 1,000 amps?
So the device isn't protected per se because the current goes through the package. So the key question to look at whenever we talk about survivable currents or current ratings, and even for continuous currents, is fundamentally a thermal problem. So this device can survive very high currents for very short durations. It's a copper lead frame. Copper has pretty good mechanical properties as far as immunity to high current events. So that's a very complicated question that we really need to look at the mission profile of the sensor as well as the thermal considerations in your board design and operating environment.
Okay, could you comment on this? The error curve showed at the low end having very large errors.
Right, so this is simply because of offset. So if I have a full scale signal, my output is going to be basically at either supply or ground. If I have a small current input, then I'm going to have a very small output signal for that same current, right? So at 0 amps, I actually have 0 output. If even I have a 1 millivolt output error, my error is infinity, right? So the error always goes higher at low current because of offset. And this is really the dynamic range question. And so what's critical here for getting high dynamic range or for pushing this vertical asymptote as far to the left as possible is to keep a low offset system. And this is really where the 1100 excels, as it has the industry's lowest offset and lowest offset drift over temperature. And so the 1100 is really focused on giving you that optimized dynamic range and pushing that curve to the left.
Okay. Some current sensors I've used have a ratiometric output. When should I use a device with a fixed versus ratiometric sensitivity?
So a ratiometric device simply means that the sensitivity changes with supply. Where this works really well is in systems where the analog supply to your sensor is the same as the full-scale reference to your ADC and is expected to vary widely. That way, if that supply changes, your sensitivity matches your ADC scale change. Now, in a system with a fixed reference, or an ADC, something like an embedded microcontroller ADC, or an ADC with its own internal reference, or just with a very good reference that doesn't drift much, ratiometry will actually induce additional error as you get poor PSRR, and your sensor gain will actually change as your switch mode power supply, your LDO powering it drifts around over time.
Is there a reason that higher bandwidth devices could not be made? In particular, they're looking for something well above 100 kilohertz at 3 dB.
So higher bandwidth devices can be made. The primary trade-off whenever you make a high bandwidth device is some things that we have to do in the circuitry to accomplish low offset. So typically, if you look at a Hall sensor itself has usually 10 megahertz or so of bandwidth. So it's not an issue getting a Hall sensor to high bandwidth. And there's obviously op amps and signal chains that reach that bandwidth as well. So absolutely, that's a product that could be made. What you find is that a high bandwidth device typically will not have excellent dynamic range or low offset and low temperature drift. So I would imagine, a high bandwidth device is probably pretty interesting to us. These particular devices are really focused at enabling higher precision. And so that means that it needs to have a little bit lower bandwidth.
Well, I'm afraid we've run out of time. If you asked a question that was not answered yet, we will be in contact with you soon to answer all of your questions. That concludes today's presentation. On behalf of Electronic Design, I'd like to thank Texas Instruments for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.